Well, Mr. Sams, we're back. What's wrong?
How'd you get up there?
What do you mean up there?
Well, it's usually the other way around.
Oh, it's a matter of perspective, actually. See, I grew about 12 inches. Oh, there is a chair there. Okay, yeah, well, I see there's a pretty cool backdrop behind us.
Yeah, that's the periodic table.
Periodic table of the...
Of the elements.
Elements.
Yeah, we're going to be talking about elements and
Elements
compounds
today.
and mixtures.
Yeah, so we want to learn about elements.
Yeah, so there's
Like-
roughly...
So here,
I don't know if you can see the number on there.
yeah, lots of elements on the periodic
Yeah,
table. There's
roughly
molybdenum.
100-ish.
I love that. It's my favorite element.
Molybdenum.
Molybdenum.
Yeah.
Yeah, and of course we've got arium, better known as
Gold.
So it's very cool, the periodic table. So we're going to learn about the elements
Yeah.
on the periodic table.
And how they...
So we've got elements. That's like from the periodic table, compounds, and the mixtures, right?
Yep.
So that's what we're going to be talking about today. Okay.
All right.
So, like, what's an element?
Well, it's atoms.
Yeah, elements are actually atoms. So we've got these things called atoms, and then we have this table called the periodic table. This is actually a pretty cool picture. This was, when I was like in high school, do you know this picture did not exist? Any ideas why?
Because you're old?
Yes, well that's true
Oh.
too. Yeah, but you know, this is an amazing picture right here of atoms. When I was like in high school, they didn't actually have pictures of atoms because the...
Did they have cameras?
They had cameras, but they did not have electron scanning tunneling microscopes.
Oh, that's what it is.
And so these are actually pictures of some atoms in a crystal structure.
Yeah.
So the if you will, the microscope technology has not been around that long.
Yeah. Now here's all of our elements on the periodic table. Now you can have one atom of an element and it's still that element. Or you can have a gazillion atoms of that element and it's still that element. And it still maintains the properties of that element.
Yeah, and so we have different sizes of elements. So even though they're very tiny, elements are tiny, that would be one atom, and this would be an atom of a larger one like radon. They're just different sizes. So that's something just to say about it. I'm not sure if that's that critical. Then we have this thing called a compound, and so this is a sort of a diagram of a possible compound.
Yeah, it looks like we've got one atom in the middle, that kind of grayish colored one.
Yeah.
And then we've got two out on the sides. I'm guessing that's probably carbon dioxide.
Yeah,
oh,
it
hey,
is.
look at that in the URL there. It
CO2.
says carbon dioxide.
So it's CO2. So
Yeah.
what is a compound? Oh, here's actually the Lewis dot structure. We'll learn more about what that is. But there's actually kind of like what we call a double bond. Hard to see that there's a double bond in there. And it's not like there's two lines there. This is actually a more atomic representation of what you're seeing.
Yeah, a
there.
compound is when you just take two or more elements and you bond them together with a chemical bond.
All right, so let's write that down. Two or more elements. Pen's doing a weird thing.
Yeah, it's doing
Elements
weird things.
bonded together, right?
Yeah.
Good.
What is your pen doing?
I don't know.
That's
It's doing
kind of fun,
some
though.
odd things.
Yeah.
Okay. All right. So when we look at elements in a compound, we can actually look at different elements, or compounds, pardon. We can figure out how many elements are there.
Right.
So
and we do that from its chemical formula that's
yeah.
listed
So
here.
these are called the chemical formulas. CO2 is carbon dioxide. We'll
Right.
learn more about how to name them. But how many? What elements are in carbon dioxide?
Well, I see a carbon
which is C,
and...
which is carbon.
Uh-huh.
Okay, good.
And then there's oxygen as well.
There's oxygen. Okay, and how many different carbons and how many different oxygens do we have, Mr. Sam?
Well, it looks like one carbon.
Okay, there'd be one of these.
Now, notice that there's one of them, but there's no one in the formula.
Yeah,
we never write ones in
There's
chemistry.
kind of like there's
Chemists
a one
are
there. but-
lazy.
yeah, so it's just CO2. O2.
Yeah, two oxygens,
That
yeah.
would be two oxygens.
Yep. Now, how do I know that's not cobalt?
Well, because the carbon is capitalized and the
Right.
O is also capitalized.
Right.
And cobalt is big C, little o. So the
Oh.
convention is if you have a single letter, like fluorine, for example, is simply F. But if you want to, maybe the best example, but if I have tellurium, which is TE, the second letter kind of indicates it. There's no element T, but whatever. So
Yeah, so the first element, or the first letter is always capital, the second letter is always lowercase.
if
So
there's a second letter.
If there's a second letter. If you see two capital letters together, you know that those are two separate elements. So those of you who write in all capital letters, you're going to have to fix that while you're in chemistry.
Yes, that's true. Now we have a different one.
And we have another.
So we have a second compound. This one has three elements. We have carbon, hydrogen, and oxygen.
Uh-huh.
Okay, so how many carbons have I got?
Looks like there's 6 carbons.
Okay, and hydrogens?
12 H's.
And oxygens?
There's 6 of them.
6. Very good. Okay, we have a third one. Oh, this is a weird one. This is
yeah.
calcium phosphate.
Huh.
Calcium phosphate.
So that C right there, that's not carbon?
No, that's not carbon. It's got the A next to it. So that would be Ca, which is calcium.
Oh, okay, so that lowercase goes with the C, and that makes that
Right.
calcium.
And then this
okay.
3 means that there are actually 3
okay.
calciums.
3 calciums, all right.
Okay, but now I've got this parentheses. I've got
Yeah.
PO4, and then there's this 2 right here. So we actually have 2 different elements, P and O. P is phosphorus. Phosphorus. You ever played with phosphorus?
In high school, yeah.
It is
back
really-
before they banned it.
They banned it. Yeah, I bought someone got in big trouble. Okay, that's an interesting story. Okay, so how many phosphoruses are? Well, there's no number here, so you'd say there's a 1 here, right?
Yeah, but that
But there's
little
this
2.
2. That 2 really means that everything inside this parentheses is doubled.
Yeah, it's kind of like the distributive property. You
Yeah,
kind of multiply
exactly.
it through. So there's 2 phosphoruses, phosphori.
I don't know how you'd say that. And oxygen would actually be a big number.
Yeah,
There'd
it's going to be 8.
8
4
of those.
times the 2 there.
Yeah, all right. And let's do, I think, one more. Ammonium phosphate.
Oh, yeah.
NH4
Okay, so there's that
Got the
parentheses again,
with
yeah.
that 3 thing going
So
on.
it looks like there's going to be 3 N's, which is nitrogen.
How many hydrogens you got?
4 times 3 is 12. So
Yeah.
12. Don't add those together. Don't add them. That's
Not 7, it's 12.
multiplied. Yeah.
Yeah. Mm-hmm.
Yep.
Phosphorus.
Phosphorus, there looks like there's just one of them.
One, and then nitrogen, or not nitrogen. what is it?
Oxygen.
Oxygen, thank you.
Yep.
Would be just simply
4.
4.
Now, why aren't there 4 phosphoruses?
Because there's no parentheses by the P and the O here.
Right. Oh, okay.
So that's not
So
there.
that 4 only applies to the element that it's kind of touching.
That's correct.
Oh, okay. Okay, we're going to look at a heterogeneous mixture. Now, the prefix hetero means different. So this is a different mixture, meaning it's not a uniform distribution of the things that are in the mixture. So this is just plain old water. Okay, and here I have, looks like some pinto beans, some white beans, and some corn. Now, these are all different substances. Okay, now if I throw them in there, they are not uniformly distributed. I can go to a particular place in that mixture and I can see just a pinto bean. Or I can see just a piece of corn. Or I can see just a white bean. Or up at the top here I can see just some water. Okay? And I can put more and more in, and no matter how much I stir it, this is never going to be uniformly distributed unless I really, really mash it together. Cook it to death and turn it into mush. But for now, that's a heterogeneous mixture. It is not uniformly distributed. Now the next one we're going to look at is a homogeneous mixture. Now homogeneous mixture, the prefix homo means same, so this is going to have the same distribution of the compounds throughout. Now, I'm just going to take some salt, which is nice and soluble in water, and I'm going to pour it in here. Now, notice what happened. It sunk to the bottom. Currently, this is a heterogeneous mixture because the salt is not uniformly distributed. I can go up here, and it's not going to be very salty water. Down at the bottom, it might be slightly salty. There's going to be some salt hanging around the bottom. But if I stir this thing, and I get all that salt to dissolve, what's happening is those salt crystals are breaking up, and they're breaking up into individual sodium and chloride ions.
We call that dissociation, boys and girls.
Exactly. We'll talk more about that in Unit 9.
Yeah.
But I'm going to stir this all up. Now notice there is no more salt on the bottom of the beaker. But now, no matter where I go in this beaker, there's going to be an even distribution of water molecules and sodium and chloride ions in there. It's uniformly distributed. It has the same composition throughout, so we call that a homogeneous mixture. Another name for that is a solution.
Guys, this last piece right here is to talk about just kind of matter as a general thing. We learned about matter in the first podcast, but really matter can be divided into 2 different ways. Mm-hmm. There's pure substances. I don't think we've used this term yet, but a pure substance or a mixture. Now, we just a minute ago talked about mixtures, right. But let's talk about pure substances for just a second. There are 2 kinds of pure substances. There are elements and compounds. And we talked about that just a little bit ago. And the way to break them apart, to break a compound apart, I don't know if you see this arrow, that's kind of important, is by a chemical separation.
Yes.
For example, if you have water and you want to break it apart, The only way to do that is to add electricity.
Yep.
Well, maybe not the only way, but certainly the easiest way
Right.
is if you add water, it will split that part.
Right, and it'll split it up into hydrogen gas
Yeah,
and oxygen
it
gas.
actually turns into H2 and O2.
And if you can figure out a way to do that efficiently and then power things off the hydrogen, you'll make $1 gazillion
Oh,
in
you
the
will be-
coming 20,
yes.
50 years.
No doubt. And then mixtures, of course, which we just got through with the little video clip, is there's two kinds of mixtures, homogeneous and heterogeneous, and you just saw the difference, by the way. And then Mr. Sims at the very end alluded, he had that salt water, and that salt water is considered a solution. How is a solution different from all homogeneous mixtures? Mr.
Well,
Sims?
solutions, we classify those as things that are dissolved in water. It's a homogeneous mixture dissolved in water. That's a solution.
Actually, that's a aqueous solution.
That's
Mr.
true.
Sims.
Yeah.
They're just dissolved. Actually, solutions, the size of the mixed particle is uber small.
Yeah, really, 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 really small.
So that's really the key thing.
Yeah, and we'll talk more about some things that are kind of in an intermediate state between there in future lessons.
Okay.